Very good morning to all of you. So, last time we were discussing the sufficient conditions for having allele decomposition for a given matrix A. So, the first result has been understood that a matrix A can be written as product of a lower triangular matrix and upper triangular matrix if all n leading principal minors of the n cross n matrix are non-singular. So, when you try to identify an allele decomposition by writing a pseudocode or by writing a code in your MATLAB, so you need to put check, you can say, you can put check and you try to note down that you try to calculate all the principal minors AK. So, what is AK is? AK is the leading principal minor of order k cross k, and how will you obtain is AK is nothing but is determinant of this is A11 to A let me write it clearly. Okay, let me write it. Okay, let me go to the next page. So, what you can put the check in, you need to check, okay, for A is equals to LU. What you need to check in writing pseudocode is whether that AK is non-singular or not, is non-singular. So, you need to verify this, then only you should proceed for finding LU decomposition. So, whether you are going for finding Dirichlet or Crowds, okay, other type of LU decomposition, then you must check that all minors, all leading principal minors of order k are non-singular, okay, for every k. Okay, so what is AK? So where if I wish to write here AK, what is AK is clearly is determinant of, you have k rows A11 to AK1, A12, and you are going till kth column, and you are having AKK, and this is AK2 and so on. So, you are making the block starting from A11, you are going up to kth row and kth column. Okay, so you need to check for every k. So, for you can say for k is equals to 1, 2, 3 and so on till n. So, if any of them is singular, then you can straightforward break the loop, okay, and then you can say that the given matrix does not have LU decomposition. Okay, for a non-singular matrix, if all leading principal minors of order k are non-singular, okay, then you will proceed for finding Dirichlet decomposition and Crowds decomposition. Okay, that's for check. You can say here Dirichlet or Crowds decomposition. You can say Crowds. Where in Dirichlet, what you have seen, the lower triangular matrix has diagonal entries, all are equals to 1. Whereas in Crowds decomposition, instead of in lower triangular, that he has considered the upper triangular matrix with its diagonal entries are equals to 1. Okay. Moreover, for Cholesky decomposition, so you have Cholesky decomposition. If you see here the result, which states that if A is real, symmetric and positive definite, then it has a unique factorization, which is given by A is equals to L into L transpose, in which L is lower triangular with a positive diagonal. That can be very much clear, because whenever L into L transpose you will obtain, and you see the diagonal entries, they are nothing but the positive, that's squared. Okay, that will be the squared one, positive diagonals. Okay, so you have, if you wish to see an example for this, okay, so let's see example. What do you mean? So what I have is, let's okay, I will come back to here. Okay, let's add one base here. Okay, so A is equals to L into L transpose. So let's say for 3 cross 3, how it will looks like is L11 0 0, L21 L22 0, L31 L32 L33 time its transpose. So that is L1100, L21 L22 0, L31 L32 L33. So once you multiply both sides, right side, in the right side, what you will get is the diagonal entries. I am only concerned right now the first diagonal entry. So when you multiply the first row with the first column, so L11 square plus other entries are 0. So some of the entries will be here. Okay, now I am concerned with this. So how will you obtain this entry is second row multiply with second column, right? So that is L21 square plus L22 square, and some other entry here, non-zero, maybe 0, I don't know currently, because it depends on the matrix. Now I am not concerned about these entries. These may be 0, maybe not be 0, but this last entry, how will you obtain, is last row multiplied by the last column is squared of all numbers. So L31 square plus L32 square plus L33 square. So you can look at, so since this is a non-singular matrix, so Lii are non-zero. Okay, I is equals to 1, 2 and 3 for this special case. Okay, so L11 square is always strictly greater than 0. So L21 may be 0, may not be 0, but L22 is non-zero, L22 square is greater than 0. So second number is, so second diagonal entry is also strictly greater than 0. Similarly for the third diagonal entry, okay, on here. So this is greater than 0 always. This is also greater than 0 and this is also greater than 0. Okay, so if you look at here, so it's very clear that L11 square is strictly greater than 0. Okay, L21 square plus L22 square is strictly greater than 0. L31 square plus L32 square plus L33 square is strictly greater than 0. Irrespective of, see, whether the value of L21 is 0 or non-zero, L31 and L32 are maybe 0 or may not be 0, but we are sure that Lii are non-zero numbers, so but the square is always strictly greater than 0. So diagonal with positive diagonals. Okay, so it also says that A has the diagonal entries which all are with positive sign. So you can say all aii's are strictly greater than 0 from here. Okay, right. So what is here is, so to important to note that here is if A is real and symmetric and positive definite. So why I am considering here singular non-singular matrix? Because of definition of positive definite. So what when you will say a matrix is positive definite. Okay, so let me add that here. Okay, so I want to state that when a matrix is said to be positive definite, so a matrix A, okay, of order n, so I just write here n cross n, is said to be positive definite if for every x in Rn and non-zero vector, for every x in Rn which is non-zero, that x transpose Ax is strictly greater than 0. Its equivalent definition, if I wish to state here, is, okay, from here, okay, its equivalent definition is if and only if every eigenvalue say lambda, okay, say lambda of A is non-negative, or in other words I say you take, so every eigenvalue is strictly greater than 0, cannot be negative, it's is strictly positive, I say must strictly positive. So to get this definition, you can easily say, so let's say an eigenvalue is lambda, corresponding eigenvector is x non-zero, then you apply, okay, so it's very easy to show, okay, it's very easy to show that let, okay, okay, what, so if I wish to show let lambda is such that Ax equals to lambda x, okay, so x is said to be an eigenvector and x where x belongs to Rn minus 0. So this is a concept we are bringing from linear algebra. So from here now x transpose Ax is equals to, so Ax is lambda x, so lambda is a scalar, so it is lambda time x transpose x. Okay, so what is this? This is lambda times summation of xi square, right? If you know, this is a dot product. Okay, I is equals to 1 to n, which is strictly greater than 0, which is only possible only if lambda is strictly greater than 0. So whenever you consider any eigenvalue for a positive definite matrix, it always be strictly positive. So, and you know that the determinant of a matrix is always equals to the product of eigenvalue. So product of all product of non-zero eigenvalue. Okay, so if all the eigenvalues are non-zero, so the matrix is non-singular. So whenever a matrix is positive definite, then if and only if every eigenvalue of a matrix is strictly positive. Now we have equivalent definition for a symmetric matrix. Okay, so which is known as Sylvester criteria. Sylvester criterion. Sylvester's criterion. Oh, here maybe E is there. Okay, so Sylvester's criterion says that a real symmetric matrix, so a real symmetric matrix is positive definite if and only if all leading principal minors are strictly positive. Or you can say, means in short, in other words, AK are strictly greater than 0 for all k is equals to 1, 2, 3 and so on till n. So this will give you a check when you try to develop an algorithm for finding Cholesky decomposition. So before going to investigate Cholesky decomposition for a given matrix, so you can put this as a check that, so when you need to find Cholesky decomposition, okay, so you can say for Cholesky decomposition, so you can put a check in your code. So in algorithm you can put you can say if something happens, so if what happens if AK, so you need to put this AK greater than 0 for all k is equals to 1, 2 and so on n, okay, for all k. So you can do, or you can use loop if, okay, if AK is greater than 0 for every k. So you can compute AKs, keep on computing. If AK greater than 0, you proceed to compute the next AK, okay, and so, okay, and then if once this condition fails for any k value at any stage, you can just simply come out with the message that Cholesky decomposition is not possible. Okay, so this you can put as a check in your algorithm. If AK is greater than 0 for every k equals to 1 to n. So before writing the code, so you always need to put a check. You need to verify whether the Cholesky decomposition exists or not. Okay, so here you need to have, so that is a very, you can say, second thing actually. First thing is you need to check whether A is equals to A transpose. Okay, means you need to check whether you can verify that whether Aij is equals to Aji or not. Okay, for you can say 1 less than equals to I less than equals to n for n, and for 1 less than equals to j less than equals to n. So the first you need to check whether the matrix is symmetric, then you can go for checking whether all the leading principal minors are strictly positive or not, to find out that or to verify that whether the given matrix is positive definite or not. Then if these two conditions are true, then you can go for finding Cholesky decomposition for the given matrix. Okay, right. So in the last time what we were doing an example that whether this given matrix A is positive definite or not. Okay, so it is now very easy, rather checking this abstract condition here. Now it becomes very easy to find out whether the given matrix is positive definite or not by using Sylvester criteria. So if I use the Sylvester criteria, I need to find, so here it's a 3 cross 3 matrix. So I need to identify whether A1, what is A1 is determinant of 1, that is 1, that is strictly greater than 0. Now what is A2 here is now 1, 2, 2, 4, right? So means this is one block, then another block, then complete matrix, right? Okay, so what it will be, 4 minus 4, that is 0, which is not strictly greater than 0. So here you can get out from your algorithm. Okay, so Cholesky decomposition is not possible. So it's very clear that, okay, clearly A is equals to A transpose. Okay, that is we are known. Okay, already by looking at the matrix we can verify that. Okay, and also all entries are real and A is real. Okay, whereas A2 is not strictly greater than 0, what I can say. So therefore Sylvester criteria Sylvester's criterion implies that A is not positive definite. Okay, so implies Cholesky decomposition okay is not possible. Okay, Cholesky decomposition is not possible. Cholesky decomposition is not possible here. So it is very easy now to verify whether the Cholesky decomposition is possible or not. Okay, right. So using Sylvester criteria, analytically you can for 3 cross 3 you can check whether the given matrix will have Cholesky decomposition or not. Okay, So let's go with one example for each problem. Okay, so let's have first example for deleteless decomposition. So let's consider this following matrix A. Okay, so first you need to, so this I am just here I have written directly in the form of this this matrix is equals to the right hand side. So but that is actually questionable. Okay, so what I need to first verify is, okay, I need to verify AK are non-zero, means all leading principal minors are non-singulars. Okay, so if I try to calculate, so that is A1 is 6, which is non-zero. Okay, similarly A2 is 6 minus 2, 12 minus 8. So first two row and first two column. Okay, so that is equals to minus 48 plus 24, that is equals to minus 24, which is again non-zero. Okay, let's have third leading principal minor now. Okay, what it is A3 is equals to 6 minus 2, 2, 12 minus 8, 6, 6, 3 minus 13 and 9, minus 13 and 9. So first three row and first three column. Okay, so you need to find out the determinant of this matrix. So that is equal to 6 minus 72 plus 78 minus minus plus 2 time 108 minus 18 plus 2 into minus 156 plus 24, right. So that is equals to 6 into 6 is 36 plus 90 into 2 is 180, okay, plus 2 into minus 1 132. So that is equals to 36 plus 180 minus 264. So which is certainly non-zero, that you can calculate, it's very easy. Similarly, you have to find out what is A4. Okay, so a determinant of this matrix, okay, A4. So that is, you can verify 6 minus 2, 2, 12 minus 8, 6, 3 minus 13, 9, 4, 10, 3, and the last row is minus 6, 4, 1, 1, minus 18. So again, easily you can verify that this is A4 is non-zero. Similarly, okay, like you are calculating the determinant, you have to calculate the determinant here for the entire matrix, and you can verify that this is a non-singular matrix. Okay, so you need to first verify this. So once this condition is true, then it will have certainly have deleteless decomposition, and this question is now fine here, that whether I can write this as equals to this or not. Now what you have to do is, now you carefully compare the left hand side and right hand sides. Okay, so what I have is now here, so let me add here. Okay, so if I compare, or if I wish to write both sides, so left side is you have 6 minus 2, 2, 4, 12 minus 8, 6, 10, 12 minus 8, 6, 10, right? Okay, 3 minus 13, 3 minus 13, 9, 3, minus 6, 4, 1, minus 6, 4, 1, minus 18 is equals to, what you have is 1, 0, 0, 0, L2, 1, 1, 0, 0, L3, 1, L3, 2, 1, 0, L4, 1, L4, 2, L4, 3, L4, 4 is 1, into U1, 1, U1, 2, U1, 3, U1, 4, 0, U2, 2, okay, U2, 3, U2, 4, 0, 0, U3, 3, U3, 4, 0, 0, 0, U4, 4. Now carefully multiplying the right side and equate. So on equating, so I will say on equating both sides. We get, so if you multiply the first row, okay, first row with each column, okay, so multiply on the right side L and U. So what you will, and if you compare, so if you multiply this first row with here and so on, what you will get is U11 equals to 6 from the first row, U12 is equals to minus 2, U13 is equals to 2, and U14 is equals to 4. From the first row, if you equate both sides. From the second row, if you have, that is L21 U11, that is equals to 12, right? Second row, first column. Now second row, second column, that will give you L21 U12, right, plus U22 is equals to minus 8. Now second row, third column, you have L21 U13 plus U23 is equals to 6, and the fourth entry, what it will be is L21 U14 plus U24 is equals to 10. Now from the previous value, so first from the first row what we have obtained U11 value, so this will give you L21 is equals to 2. So once you have L21 value and U12 value, from the second here, what you will get is L21 is 2, U12 is minus 2, so minus 4 plus U22 is equals to minus 8. So this will give you U22 is equals to minus 4, right? Similarly, from the third entry, if you compare both sides, so L21 is already obtained, that is 2. U13 is from the first row, that is 2. So 2 into 2 is 4 plus U23 is equals to 6. So U23 is equals to 6 minus 4, that is 2. Right? Now from the last, L21 is 2, U14 is 4. So 2 into 4 is 8. So U24 is equals to 2. Okay. So this is obtained by using the first row, all entries now. So what you have known now, L21 is known, and you know now U11, U12, U13, U14, U22, U23, U24. Okay, right. Now similarly from the third row now, so what you will get is, from the third row, if you try to compare, so L31 time U11 is equals to 3. L31 U11 is equals to 3. Right? So second row, third row, second column, what it will give you? L31 U12, L31 U12 plus L32 U22, U22, okay, plus is equals to minus 13. Right? Now third row, third column, what it will give you? L31 U13 plus L32 U23 plus U33 is equals to 9. And now last, so third row, last column, what you will get is L31 U14 plus L32 U24 plus 1 time U34 is equals to 3. So now from the first equation, L31 U11 equals to 3. Now since U11 is already known, that is 6. So what you will get is L31 is equals to 3 by 6, that is 1 by 2. Right? Now L31 U12, okay, L31 is now 1 by 2, U12 is minus 2, right? And U22 is also obtained, that is minus 4. Okay, so L31 is 1 by 2 time U12. U12 is minus 2 plus U22 is minus 4 time L32 is equals to minus 13. What this will give you is minus 4 times L32 is equals to 13 plus 1 is 14. So this will imply L32 is equals to 7 by 2 with minus sign. Right? So what is U22 we have obtained is L21 is 2. Right. That is minus 30, 9, 3. So 6 minus 2, 2, 4. Okay. So 1 by 2 into minus 2 is L31 U12, that is minus 13, right? Yeah. So this is minus 13. So minus 13 plus 1 is minus 12. So this will imply L32 is equals to 3. Yeah. Okay. Now the third equation, so L31 is 1 by 2 into U13. What is U13 is 2. You have to be careful. Plus L32. So L32 is positive sign now with 3. L32 is 3 times U23. So U23 is 2. Okay. Right. Plus U33 is equals to 9. So what this will imply is, so you have, this implies U33 is equals to, so 6 plus 1 is 7, so 9 minus 7 is 2. And the fourth entry, what it will imply is L31 is 1 by 2 into U14. What is U14 is 4 plus L32. L32 is 3 times U24. U24 is 2 plus U34 is equals to 3. So this implies U34 is equals to, so 6 plus 2 is 8. So 3 minus 8 is minus 5. Okay, right. So now we have obtained already all the entries till U33, U4. So all the entries here, first 3 rows here and in the lower triangular matrix. Similarly, you can go for the last row multiplied by first column. That will give you the L41 value. Then use it to find L42. Okay. And then use them to find L43. Okay. Right. And now substitute. So what you will get is, so now similarly obtain all other values. Okay, all other remaining values. So similarly obtain L41, L42, L43, okay, and U44 by the last row multiply by each column on the upper diagonal matrix. So what you will obtain if you arrange all the things here, so that is L21, L31, L32 and L41, L42, L43, and this is an upper triangular matrix. So this is L and this is U. Right? Okay. So similarly, you can proceed for finding the Crouch decomposition. So this can be left as an exercise for you to find the Crouch decomposition. Okay. So here is a typo error, that is L11. This is L22. Okay, and rest entries are same. So in the Crouch decomposition, you need to you need to write A as L into U, where upper triangular matrix has diagonal entries equals to 1. Okay. So again you need to go for similar. First you need to verify for a given matrix, verify that AK is strictly greater than 0 for all K is equals to 1, 2, 3 and so on till n. First you need to put that check. Then it will give you the guarantee that the given matrix A has LU decomposition. So you can proceed for finding the Crouch decomposition for the same. Okay. So similarly, now equate the coefficient, equate the entries on both sides and identifies what are these unknown values in cross decomposition. Fine, right? Okay. So this is how you can proceed. Okay, right. So cross decomposition. So here I have given you the actual cross decomposition for the given matrix. You can verify, just follow the same way what you have done for Dirichlet's decomposition by equating the entries on both sides. Okay, right. Let us take an example for finding the Cholesky decomposition. So I have the following matrix. Given matrix is this. So it is you can first you need to verify. So you have to first verify that A is real. Yes, you can check each entries are real numbers. Second verification you have to do is A is symmetric. Okay, so you can verify that whether A is equals to A transpose or not. The third thing is, which is very important, with that A is positive definite. So for this, okay, for this you are AKs are strictly greater than 0 for every k is equals to 1, 2 and so on n. So you have to first check all these three, verify the things, and then you can only proceed. Okay, right. So it's very clear from the matrix that A is real. Yes, A is symmetric. You can verify this is A equals to A transpose. That is very easy to verify. The third thing is A is positive definite or AK is greater than 0. So you can verify one by one. So what is A1 is, this is 60, that is 60. What is A2 is the first two row and first two columns. So that is 60, 30, 30, 20. So 60, 30, 30 and 20. So what is this determinant value is this 1200 minus 900, that is equals to 300, which is strictly greater than 0, right? A1 is also strictly greater than 0. What about A3 is, you have 60, 30 is 20, this is 30, 20, 15, 12, 15, 12, 20, 15 and 12. So you can also find this determinant. What is this? Is 60 time 240 minus 300 minus 30 time 360 minus 300 plus 20 time 450 minus 400. What will equals to it is? It is minus, so first entry 60 into minus 60 is minus 3600 and the second entry is minus 1800 and the third entry is 1000, which is certainly am I correct here? 60 time 240 minus, this is 240 minus 15 into 15. So that is, this is not right here. And that's 15 and 7 is 225, right? Okay. And this is minus 30 times 360 minus 300. That second entry is correct. The third entry is 20 into 450 minus 400. So I wish to find out now the what is this sum equals now. Okay, what is this sum equals? So the A3 is equals to, so 60 into 240 minus 225. So 240 minus 225 is 15. So 15 into 6 is 900, right? Minus 1800 plus 1000. So that is equals to 100, and which is strictly greater than 0. So all leading principal minors are strictly greater than 0 for the given matrix. So third condition is verified. So you can proceed for finding. So hence what you can say now is, so from above we say that we have that from above we have that the given matrix A has Cholesky decomposition. Okay, that is, there exists a lower triangular matrix, L such that A is equals to L into L transpose. Means this implies, that is this 60 20, okay, 60 30 20 30 20 30 20 15 20 15 and 12 can be written as product of, so you have L1100, L21 L22 0, L31 L32 L33 and its transpose now L1100, L21 L22 0, L31 L32 L33. Now again, in the same way what we have done for finding the Dirichlet's decomposition and cross decomposition, you equate the both sides and find out what are these unknown values. So if I go through it once, okay, let me find out some of the values, rest I will leave for an exercise. So what you can do is, so you have if you multiply first row with first column, what it will give you is L11 square is equals to 60. Okay, second first row second column is L11 L21 is equals to 30. L11 into L31 is equals to 20. So from here you can go for L11 is equals to square root of 60, positive square root. Similarly, L11 is square root of 60, so L21 is equals to 30 by root 60. So what is root 60 is? So you can go for that 30 by root 60. You can simplify it. Okay, what it will be is, right, okay, 2 time, so you multiply and divide by root 60 here. So 2 or not 2, root 60 by 2, and that is equals to, you have root 60 is 15 into 4 is 60, so square root of 15, so that is L21. From here L31 is equals to 20 by root 60, so that is equals to root 60 by 3, right, and so on. Similarly, from the next row, L21 times L11 will give you 30. From L11, you known value, you can get L21. Okay, from the second row, what you have is L21, L11 is equals to 30. So L21 is equals to, so already this is already known here. So L21 is equals to again square root of 15. So there is nothing new you are finding. Okay. So from the second row, second column, what you will have is L21 square plus L22 square. So L21 square plus L22 square is equals to 20. So from above, L21 square is 15. So L22 square is 20 minus 15 is 5. So L22 is equals to positive square root of 5. So again, you are saying it's positive diagonal. Okay. Similarly, from the third row, from the second row, third column, what you will obtain is L21, L31 plus L22, L32. Okay. L21, L31 plus L22, L32 is equals to 15. Now you know the value of L21, that is square root of 15, L31 square root of 60 by 3, L22 is just known. So all these you can substitute and find out the value of L32. So similarly, you can proceed for finding other unknowns, and what you will get is the following matrix, right? So these things you can verify the both side. Okay, right. So in the okay, so in the what is the next here is, okay, so what we are going to learn is next is basic Gauss elimination method, operation count. Okay, and we'll see the sum of the why this Gauss elimination method fails, and what will be the substitute, or what are the adopted pivoting strategies for improving the Gauss elimination method. Okay, fine. Thank you.